66 million years ago, on an otherwise ordinary morning, the sky above what is now the Gulf of Mexico split open. Not metaphorically, not poetically, literally. A rock the size of a small city traveling at roughly 20 kilometers per second punched through Earth's atmosphere so fast that the air in front of it had no time to move out of the way. It compressed, it superheated, and in the final fraction of a second before impact, the ground below didn't just shake, it vaporized. The explosion that followed was not measured in tons of TNT or even megatons. It was measured in billions of them. In a single instant, a world that had existed for 165 million years, a world of giants, of thunder lizards, of creatures so magnificent they seem almost impossible, was handed a death sentence. And the terrifying part, it wasn't even the impact itself that killed them. What happened in the hours, days, months, and centuries that followed that impact is one of the most catastrophic and complex and most scientifically fascinating stories in the entire history of our planet. It is a story about fire raining from the sky, about a darkness that swallowed the sun for years, about acid oceans and poisoned air and the slow grinding starvation of nearly every living thing on Earth. It is also, quietly, a story about survival, about the stubborn, almost miraculous persistence of life even at the very edge of annihilation. And if you think this is merely ancient history, something that couldn't possibly concern you today, consider this. The very fact that you are sitting here watching this video capable of curiosity and thought and wonder is a direct consequence of what happened on that morning. Your existence and the existence of every human being who has ever lived traces back in a straight and unbroken line to the day a rock from outer space nearly ended everything. To understand the full weight of what happened, we first need to go back. Not just 66 million years, but much farther, back to a time when the solar system itself was still young and chaotic. When our sun first ignited, roughly 4.6 billion years ago, it was surrounded by a vast swirling disk of gas and dust and debris. Over millions of years, gravity pulled much of this material together into the planet we know today. But not all of it. The solar system has always been cluttered with leftovers. Fragments of rock and ice and metal that never quite found a home. Some of this wandered the outer solar system in enormous frozen clouds. Others drift through the inner solar system in orbits that occasionally, over billions of years, bring them close to Earth. We call them asteroids and comets, and for most of Earth's history, they have served as a kind of cosmic lottery. Most pass by harmlessly, some do not. The object that would eventually destroy the age of dinosaurs almost certainly originated in the asteroid belt. That wide band of rocky debris that orbits the Sun between Mars and Jupiter. Scientists believe it was part of a larger asteroid family called the Baptistina group, shattered apart in a catastrophic collision roughly 160 million years ago. The collision sent fragments scattering across the solar system, and over tens of millions of years, the gravitational influence of Jupiter, the solar system's great shepherd and disruptor, slowly nudged one of those fragments onto a new trajectory. a trajectory that pointed with terrible precision at Earth. For millions of years, this rock drifted silently through space, dark and cold, and completely indifferent to the world it was about to unmake. It was roughly 10 to 15 kilometers in diameter, about the width of a mid-sized city. It had no name then. Today, we call the event it caused the Chicxulub impact. Named after a small town on Mexico's Yucatan Peninsula that sits almost directly above the center of the crater it left behind. Now, to appreciate what happened when this object arrived, you need to understand something fundamental about the physics of cosmic impacts. When a large object moving at interplanetary speed enters Earth's atmosphere, it doesn't simply fall like a stone thrown from a rooftop. At 20 kilometers per second, roughly 70 times the speed of sound, the asteroid was moving so fast that the interaction between it and the atmosphere was essentially explosive. The air molecules in its path couldn't get out of the way. They piled up in the front of the rock in a shock wave of compressed, superheated plasma that reached temperatures comparable to the surface of the sun. By the time the asteroid reached the surface, it was already wrapped in a column of fire. It was, in every meaningful sense, a weapon. The impact site was not random. The asteroid struck a shallow sea in what is now the Gulf of Mexico, landing in a region rich in carbonate rocks and sulfur-bearing minerals called anhydrite. This geological detail, seemingly insignificant, would turn out to be extraordinarily important and extraordinarily catastrophic. The energy released at the moment of impact is estimated to roughly 100 teratons of TNT. To give you some sense of what that means, the most powerful nuclear weapon ever detonated by humans, the Soviet Tsar bomb, released about 50 megatons of energy. The impact was roughly 2 million times more powerful than that. In less than a second, the asteroid bored a hole into the Earth's crust more than 30 kilometers deep and roughly 150 to 200 kilometers wide. The rock and water and sediment at the impact site didn't just explode outward. They were blasted upward into space, forming a curtain of molten and vaporized debris that rose above the atmosphere and spread around the entire planet. The immediate devastation in the region surrounding the impact site was, by any measure, total. Within a radius of several hundred kilometers, there was simply nothing left. The shock wave traveling through the ground triggered earthquakes of a magnitude the modern world has never seen. Estimates suggest they registered somewhere between magnitude 10 and 11, strong enough to shake the entire planet. The ocean floor around the impact site collapsed, sending a mega tsunami, a wave unlike anything in recorded human experience, radiating outward in all directions. Geological evidence of this wave, a layer of chaotically disturbed sediment called a tsunami deposit, has been found as far as north as the interior of Texas and as far as east as the Atlantic coast. But as catastrophic as all of this was, it affected only a fraction of Earth's surface. The true global extinction, the one that would ultimately kill more than 3/4 of all species on the planet, came not from the impact itself, but from what followed. And what followed was something that modern climatologists describe with a kind of quiet dread: a cascading series of environmental disasters, each one reinforcing the next, each one more difficult to survive than the last, that collectively transformed the entire biosphere of our planet in the space of just a few years. The first disasters arrived from the sky, when the asteroid struck and vaporized billions of tons of rock. That material was hurled upward into the atmosphere and beyond. Some of it actually escaped Earth's gravity entirely, but most of it, vast quantities of superheated molten debris, glass spherules, and mineral dust, arced upward into the Earth atmosphere and then fell back down, distributed across the entire planet within hours. As this eject re-entered the atmosphere, the friction generated by each individual particle falling through the air produced an enormous amount of heat. Scientists estimate that the global re-entry of this debris may have briefly raised surface temperatures high enough to ignite wildfires across entire continents. Forests that had never experienced human fire, that had stood for millions of years, burned. This global firestorm added its own enormous quantities of soot and ash to the atmosphere, compounding what was about to happen next. What happened next was the darkness. Within hours of the impact, the combination of dust, ash, soot, and sulfur dioxide gas, the latter released in catastrophic quantities because the asteroid struck those sulfur-rich anhydrite deposits, had begun to form a global atmospheric veil. Over the following days and weeks, this veil thickened. Sunlight, which had nourished life on Earth for billions of years, began to fail. Not to dim, not to weaken, to fail. Scientists modeling the aftermath estimate that for months and possible for several years, the Earth's surface may have received close to zero direct sunlight. The sky would have been perpetual dark, the way it is during a total eclipse, except there was no moment when the shadow passed and the sun returned. Day and night become indistinguishable. A deep, killing cold descended over the planet as global temperatures plummeted by an estimated 10 to 20 degrees Celsius, and in some regions considerably more. This period, now called the impact winter, was not winter in any familiar sense. It was a darkness that lasted not for weeks but for years. And in that darkness, the foundation of almost all life on Earth began to collapse. That foundation was photosynthesis. Plants convert sunlight into energy, and in doing so, they produce the oxygen and animal breathe and organic matter that forms the base of nearly every food chain on the planet. Without sunlight, plants died. Not gradually, not selectively, but comprehensively. Across the entire planet, the great forests and meadows, that ferns and flowering plants that had evolved over hundreds of millions of years began to wither and die. Within months, the landscape of Earth was transforming from a living, breathing world into something that resembled a graveyard. With the plants went the plant eaters. And when the plant eaters went the predators that hunted them. The collapse cascaded through every food web on Earth and ruthless, mechanical efficiency. But it did not stop there, because the ocean, which many people assume would have been somewhat sheltered from the atmospheric catastrophe unfolding above, was experiencing its own version of the disaster. The same darkness that was killing plants on land was killing phytoplankton in the sea. Phytoplankton, microscopic photosynthetic organisms that live in the upper layers of the ocean, form the base of virtually every marine food chain. Without sunlight, they died too. As they died, the entire ocean ecosystem began to unravel from the bottom up. The sulfur dioxide and nitrogen oxides blasted into the atmosphere by the impact weren't just blocking sunlight. They were also combining with water vapor to form sulfuric acid and nitric acid, which fell back to Earth as acid rain. This acidification struck the oceans with particularly ferocity. The ocean surface waters become measurably more acidic within years of the impact, dissolving the calcium carbonate shells of ammonites, mollusks, sea urchins, and microscopic organisms called foraminifera that had thrived in Earth ocean for hundreds of millions of years. These organisms were not merely dying. Their very ability to build shells and skeletons was being chemically dismantled. The fossil record from this period shows an abrupt and nearly total disappearance of shell-forming marine life, a boundary so sharp and so universal that geologists can't identify it in rock formations or even continent and in ocean cores drilled from every basin. This boundary, this thin, dark line in the rock, has a name. Scientists call it the KPJ boundary, short for the Cretaceous-Paleogene boundary. It marks the exact moment preserved in stone, where the world before the impact ends and the world after begins. In many locations, it appears as a thin layer of iridium, a metal that is vanishingly rare in Earth crust but abundantly present in asteroids. This iridium layer, found in rocks all over the world and at the same time geological level everywhere, was one of the first clues that led scientists to the asteroid hypothesis in the 1980s. The physicist Luis Alvarez and his geologist son Walter Alvarez noticed this anomalous iridium layer in the early 1970s and proposed something radical: that it was the fingerprint of an extraterrestrial impact. The scientific community was initially skeptical, deeply skeptical, but the evidence, as it accumulated over the following decades, became impossible to ignore. The discovery of the Chicxulub crater, itself named later in the early 90s, and it arrived not from a dramatic excavation but from the unlikely source of petroleum exploration data. Mexican geologists working for Pemex, the national oil company, had drilled boreholes in the Yucatan Peninsula in the 1970s and found peculiar rock formations, shocked quartz, glass beads, and a circular gravity anomaly buried beneath layers of sediment that they couldn't explain. When scientists Penfield and Camagro revisited this data in 1991 and connected it to the iridium layer and the Alvarez hypothesis, the pieces suddenly fit together with startling precision. The crater, now confirmed to be approximately 180 to 200 kilometers in diameter and buried beneath kilometers of younger rock and ocean sediment, was the scar left by the end of an entire geological era. It is one of the largest confirmed impact craters on Earth, and it sits almost perfectly centered at the edge of Yucatan Peninsula, its shape partially preserved on land, partially hidden beneath the Gulf of Mexico. Understanding who died in this event, and crucially why some things survived while others didn't, requires us to think carefully what about the world looked like before the asteroid arrived. The Cretaceous period, which lasted from roughly 145 million to 66 million years ago, was in many ways the most spectacular era in Earth's biological history. The planet was warmer than it is today, with no polar ice caps and shallow inland seas covering large portions of North America, Europe, and Asia. The continents were in different positions. What would become India was an island drifting northward towards Asia. South America and Africa had only recently separated, and the Atlantic Ocean was young and narrow. Into this warm, rich, geological active world, evolution had produced an astonishing diversity of life. The dinosaurs, of course, are the most famous inhabitants of this world, and they had been the dominant large land animals for roughly 165 million years by the time the asteroid arrived. They were not the slow, cold-blooded, dim-witted creatures of early popular imagination. Modern paleontology has revolutionized our understanding of dinosaurs, revealing them to be dynamic, behaviorally complex animals, many of which were warm-blooded, socially organized, and in some lineages covered in feathers. The Tyrannosaurus were apex predators of extraordinary capability. The Hartsaurus were herding animals that communicated through elaborate crests of their skulls. The long-necked sauropods were the largest land animals that have ever existed, some reaching lengths of over 30 meters. The Cretaceans horned dinosaurs like Triceratops traveled in herds and possibly used their elaborated horns and frills for species recognition and display as much as for defense. This was a world teeming with biological sophistication, and it was about to be dismantled with ruthless efficiency. In the immediate aftermath of the impact, the largest animals suffered the most. This makes intuitive sense when you think about energy demands. A large animal requires enormous amounts of food to survive. A Tyrannosaurus rex needed to consume hundreds of kilograms of meat on a regular basis to fuel its massive body. When the food chain collapsed, when the herbivores starved because the plants were gone, and when the carnivores starved because the herbivores were gone, the largest animals simply had no margin for error. They could not reduce their energy requirement enough to wait out the darkness. They starved, they froze, they died in their millions and then in their billions across every continent on Earth until the last representative of each non-avian dinosaur lineage drew its final breath and disappeared forever from a world they had ruled for longer than our minds can truly comprehend. But here is where the story becomes not just tragic but scientifically fascinating. Because not everything died. And the question of what survived and why is in many ways as important as the question of what was lost. The KPJ extinction was devastating, wiping out an estimated 75 to 80% of all species on Earth. But that means 20 to 25% of species survived. Something was different about them. Something gave them an edge in a world of darkness and cold and acid rain and collapsing food chains. And when scientists look carefully at the survivors, a pattern begins to emerge. Small body size was one critical advantage. In a world where food was desperately scarce, a small animal required far less of it to survive. The mammals of the Cretaceous period were almost without exception small. The largest were roughly the size of a modern beaver. They had lived in the shadow of the dinosaurs for millions of years, mostly nocturnal, mostly insectivorous or omnivorous, hiding in burrows and under logs and in the root systems of trees. Their small size, their burrowing behavior, and their dietary flexibility turned out to be extraordinary survival advantages in the post-impact world. They could eat insects, fungi, seeds, and decaying organic matter, food sources that persisted even after the plants were gone and the large herbivores had vanished. The survivors of the Cretaceous also included the ancestors of modern birds, the avian dinosaurs, which had already evolved a suite of features that would serve them well in the disaster. Small body size, flight, and the ability to exploit a wide range of food sources allowed many bird lineages to survive while their giant ground-bound cousins perished. Turtles and crocodilians survived, likely because of their ability to survive in aquatic environments, their tolerance for low temperatures, their slow metabolism, and their capacity to enter periods of dormancy. Some lizards survived. Many insects survived. Sharks and rays and certain bony fish persisted in the oceans. And in the deep ocean, far from the disruption of the surface, many organisms endured the disaster in relative isolation. The recovery of life after the KPG extinction is a story of almost unimaginable biological creativity. In the immediate aftermath, the first few thousand years after the impact, the world was bleak. The darkness slowly lifted as the dust and aerosols settled out of the atmosphere. But what it revealed was a transformed landscape. Forests that had taken millions of years to develop were largely gone. Soils stripped of their plant cover were eroding rapidly. Rivers were choked with sediment. The world smelled of sulfur and ash and rot. But in this devastation, a kind of ecological vacuum had been created, and life, persistent, creative, endlessly inventive life, began to fill it. The mammals, freed from 165 million years of ecological suppression by the dinosaurs, began to diversify with extraordinary speed. Within 300,000 years of the extinction, an eye blink in geological time, the first large mammals had appeared. Within 10 million years, mammals had evolved to fill almost every ecological role that the dinosaurs had vacated. They became large herbivores, large predators, burrowers, swimmers, gliders, and climbers. The diversity of mammals in the Eocene period, roughly 55 to 34 million years ago, rivals anything the Cretaceous had produced. And within this mammalian radiation, this explosive diversification of a group that had been small and marginal for its entire existence lay the lineages that would eventually lead to primates. And with the primates, eventually to the genus Homo, and within Homo, eventually to you. This is the part of the story that should make you pause. The rise of human intelligence, of human civilization, of art and science and philosophy and technology, all of it traces in one unbroken biological thread to the survival of a small furry burrowing mammal in the dark years after the asteroid struck. If the impact had been slightly less energetic, the non-avian dinosaurs might have survived. And if they had survived, this is every reason to think they would have continued to dominate the large animal ecological niches of the planet, just as they had for the previous 165 million years. The mammals would likely have remained small and marginal. Primates might never have evolved. Humans would certainly not exist. The asteroid that nearly ended all life on Earth is also, in the most profound and literal sense, the reason that any human life exists at all. The science of the Chicxulub impact has continued to deepen and surprise in recent years. One of the most remarkable developments came in 2019 when a team of paleontologists announced the discovery of an extraordinary preserved fossil site in North Dakota called Tanis. The site, located in rock formation called the Hell Creek Formation, appears to represent the actual physical aftermath of the day of the impact. A deposit of fish, trees, and other organisms that were caught in the violent surge of water created by the earthquake and tsunami triggered by the Chicxulub impact, and buried rapidly enough to preserve details that would normally be lost. Among the most extraordinary findings at Tanis are fish with impact glass spherules embedded in their gills, microscopic beads of molten rock that rained down from the sky within the first hour after the impact, breathing organisms still alive to inhale them as they fell. If the interpretation of this site is correct, it represents a snapshot of the actual day of the mass extinction preserved in stone for 66 million years. Another recent development has sharpened our understanding of just how much the geology of the impact site mattered. The sulfur-rich anhydrite deposits at Chicxulub were not just locally significant. When the asteroid vaporized them, it released an estimated 100 billion tons of sulfur dioxide into the atmosphere, far more than any volcanic eruption in Earth history. This sulfur dioxide was the primary driver of the acid rain and, more importantly, of the aerosol veil that blocked sunlight for years. Computer models have shown that if the asteroid had struck almost anywhere else on Earth, a region of ocean floor, a granite mountain range, a carbonate plateau without the sulfur, the amount of sun-blocking aerosol produced would have been dramatically less. The extinction might have been far more limited. Some models suggest that a slightly different impact location could have resulted in an event that, while devastating regionally, might not have triggered a global mass extinction at all. The dinosaurs may have survived, or at least some of them might have. The entire trajectory of life on Earth for the past 66 million years might have been completely different. The difference between a world with humans and a world without them may have come down to a cosmic coincidence of where precisely a rock happened to land. This notion that the history of life on Earth and the existence of humanity may have been determined by a geological accident forces a reckoning with some very deep questions about contingency and fate and the nature of evolutionary history. The paleontologist Stephen Jay Gould, one of the most celebrated evolutionary thinkers of the 20th century, spent much of his career exploring this idea. He argued that if you could replay the tape of life, start the evolutionary process over from some point in the past, you would almost certainly not get the same result. Life is too sensitive to contingency, too dependent on accidents of timing and geography and circumstance, for history to repeat itself. The existence of intelligent life on Earth was not, in his view, inevitable. It was, in a very real sense, lucky. And the Chicxulub impact is perhaps the single greatest piece of evidence for this view. Here was an event determined entirely by orbital mechanics, by the gravitational perturbations of Jupiter nudging a fragment of rock into a slightly different path, by the random chance of where that path intersected Earth's orbit, by the accident of where on Earth's surface the intersection occurred. None of it was guided by any principle of biological necessity. There was no evolutionary pressure favoring the development of human intelligence. There was no cosmic plan that required the dinosaurs to die so that mammals could rise. It just happened. A rock fell, a world ended, another world began, and in that new world, after tens of millions of years of gradual change and branching and extinction and diversification, something emerged that could look up at the night sky and wonder where it came from. The study of the Chicxulub impact has also transformed how we think about the future. For most of human history, the idea of a catastrophic impact from space was either unknown or regarded as mythology, the stuff of ancient stories about fire from heaven, not a real scientific concern. But the discovery and detailed study of the Chicxulub event, combined with the cataloging of thousands of near-Earth objects in recent decades, has forced a fundamental reassessment. The solar system is not a stable place. It is full of objects that are capable, under the right circumstances, of reaching Earth. Most of them are small and would cause only regional devastation. But some of them, a small number, carefully tracked by astronomers around the world, are large enough to pose a genuine civilization risk. The good news is that for the first time in Earth history, a species exists on this planet that is capable of detecting these threats in advance and, at least in principle, doing something about them. In 2022, NASA's DART mission deliberately crashed a spacecraft into a small asteroid called Dinosaurs and successfully altered its orbit, the first demonstration in history that humanity can deflect a celestial object. This was not a stunt. It was a proof of concept for a technology that may one day be the difference between civilization surviving and civilization ending. The dinosaurs had no such capability. They had no warning, no scientist, no telescopes, no spacecraft. They simply lived their lives in a world that seemed permanent and stable until one morning it wasn't. We are, in this respect, in a dramatically better position. But we are only in this position because of science and because of the centuries of careful, patient, curious work that had led to our understanding of what happened 66 million years ago. There is something almost unbearable about the scale of what was lost in the Chicxulub impact. The non-avian dinosaurs were not merely a collection of individual species, they were an entire evolutionary experiment, 165 million years of biological innovation, ecological complexity, and evolutionary diversity built up across countless generations, wiped out in a geological instant. We will never know the full richness of what those animals were. We can reconstruct their bones from fossils, infer their behavior from trackaways and nesting sites and bite marks and the preserved contents of their stomach, but we cannot hear what sounds they made. We cannot know how they saw color, whether they dreamed, what their social structures were really like, whether any of them experienced anything that we might recognize a thought or feeling or awareness. The asteroid didn't just kill them, it erased them so completely that we can only ever know them in a fragment or shadows. And yet, the story refuses to be simply a story of loss, because among the creatures that survived the impact were the ancestors of the birds, the direct, unbroken evolutionary descendants of the theropod dinosaurs, the same group that produced Tyrannosaurus rex and Velociraptor. In the most literal biological sense, the dinosaurs are not extinct. They are sitting in your garden. They are migrating across continents in the spring. They are singing outside your window at dawn. Every bird that has ever lived is a living dinosaur, carrying in its bones and feathers and behavior the evolutionary legacy of a lineage that survived the worst catastrophe in the last 250 million years of Earth's history. There is something profoundly moving about this fact that even the asteroid, for all its unimaginable destructive power, could not completely erase what 165 million years of evolution had produced. The broader lesson of the Chicxulub impact may be this: life on Earth is simultaneously extraordinarily fragile and extraordinarily resilient. Fragile because the entire edifice of a complex biosphere, the intricate web of species, interactions and energy flows and chemical cycles that sustains all living things, can be disrupted catastrophically by a single external event. The world of the dinosaurs, which had persisted for longer than we can truly imagine, was essentially destroyed in decades. But resilient because even after such total devastation, even in a world of total darkness and acid and cold, life persisted. It persisted in small, hidden, hungry, determined forms. And from those forms, over millions of years of evolution, it rebuilt. Not the same world, nothing like the same world, but a world every bit as rich, every bit as complex, every bit as astonishingly diverse as what came before. We are part of that rebuilt world. We are the product of it. And we carry within us, encoded in every cell of our bodies, the evolutionary history of every ancestors who survived. Through the impact winter, through the acid rain, through the starvation and cold, and pass their genes forward. Every person alive today is the heir to an unbroken chain of the survivors stretching back 66 million years, and beyond that, back through the earlier mass extinction, back through the first appearance of complex animals, back through the first single-cell organisms, all the way to the first fragile molecules that learned to copy themselves in the ancient ocean of a young and dangerous Earth. The history of life on this planet is the history of narrow escapes, of near misses, of survival against odds that would seem to any rational observer hopelessly unfavorable. And yet, here we are. So, the next time you look up at the clear night sky and the stars and the occasional bright point of light that is a planet, the faint band of the Milky Way, if you are fortunate enough to be somewhere dark enough to see it, remember that the same solar system that produced the beauty you are looking at it is also the solar system that sent a city-sized rock hurtling into the world of the dinosaurs at 72,000 kilometers per hour. Remember that the gap between the world that exists and the world that might have existed is in cosmic terms embarrassingly thin. A slightly different orbit, a slightly different impact location, a slightly less sulfur-rich piece of seafloor, any of these variables changed in the slightest and the world you inhabit tonight might be populated by feathered giants and not by their distant mammalian successors. And then ask yourself the question that perhaps has no answer, but that rewards the asking. If the emergence of intelligent life on this planet was so contingent on accident, so dependent on the random fall of a rock from space, what does that tell us about our place in the universe? And how many other worlds in the vast dark ocean of stars above you may have never had their asteroid, never had their catastrophe, never had their accidental gift of an empty world waiting to be filled?